Hey everybody, video number 4 for error. It just keeps getting better and better. This one is on alternating series error bound. So the last videos were all about Lagrange error bound, which we're going to spend all day Thursday practicing because I realized you had the proof of it, you have some info on it, but you haven't applied it yet, so we'll practice that. The good news about this error bound is it's much more direct, it's easier, and it's quicker to use. Lagrange error bound is a little bit trickier, and you have to be a little strategic when you pick a maximum bound. Alternating series bound, again, it's a lot easier. It's newer to the exam, and it's less frequently assessed, but we're still going to talk about it because it does come up sometimes on free responses. Remember, when we're doing error, the goal is always to find an upper bound or a number that our error is less than. We're always wondering when we are approximating, how do we determine the quality of our approximation? Because we'll find things like a third-degree polynomial approximation or a fifth-degree polynomial approximation. And we'll plug in our value in here and we'll estimate the true function value, but we never really know how close we are. That's what error bound tells us. It gives us an upper bound for how far away we could be from the real answer after doing this polynomial approximation. All right, so to use the alternating series error bound, you have to go through 3 steps, and they're usually pretty quick to go through. So the 3 criteria that you need: first of all, the series has to be alternating, which is why it's called alternating series bound. And to be alternating, it has to be plus, minus, plus, minus, plus, minus, dot, dot, dot. Some of the series that we did were like plus, plus, minus, minus, plus, minus. It wasn't a direct pattern. That doesn't work. It has to be strictly alternating, every other. The terms have to decrease in magnitude. Now, I say in magnitude here because you're going to have positive and negative ones. Just when you do the absolute value of them, they have to be decreasing. And not only do they have to be decreasing, but they have to be going to 0. So this is kind of like the nth term test that Mr. Siddiqui did with you. You take your generator, the thing that gives you all your terms, a sub n. You take the limit as n goes to infinity, and that has to be 0. If all these 3 apply, then you may use the alternating series error bound. What the alternating series error bound says is that your error, and again, we put absolute value bars around it. We just want the magnitude. We just want the positive error. The error has to be less than or equal to the value of the first unused term. So you're going to have your polynomial, let's say p sub 3. It'll be something, truncate it at x to the third, let's say. The next term, or basically the first one that you'd cut off here, your error has to be less than or equal to that one. So again, we're using that n plus 1 here. We go to n, which in this case is 3, and we're using the n plus 1, which in this case would be 4, to talk about the error. All right, so pause the video and write down these rules. I'm just going to do this quickly through the 2 free responses. It was the first one that we ever did and the last one that we did. The most recent one that on Monday was the piecewise one. So go to those free responses and add on this part. So again, in your notebook, find this one right here. This was the first free response we did last week on series. So it had to do with e to the negative x squared. Just refresh your memory on what we even did in this problem because it's been a while and you did so many of these, some of them kind of run together. So we were finding the first 4 non-zero terms of this. We used e to the x, which we know, and we did substitution. Where's my cursor? So we plugged negative x squared in everywhere here. So then we got this approximation. Then what we did is we found the integral. Oh my God, hold on. Then what we did is we used our polynomial to find the integral of it. And then we used that to find this definite integral approximation from 0 to 1/2 of e to the negative t squared. So let's go back here. We don't really need part B, but part C is what I'm really interested in. So I did the integral of my polynomial. And our polynomial approximation was this guy right here. We did the integral of it term by term. Now, when I did the integral here, I didn't use factorials. I went right to a number. I'm going to rewrite it quick with factorials because it's going to make it a lot easier to pick out the pattern. That's the nice thing about factorials. And then I'm going to plug a half in. Now, the reason I'm going to do this is, remember, in order to use the alternating series error bound, I have to find a rule for a sub n. I need a generator in order to do this. And right now, I just have a bunch of terms. I don't know what the general term is, and I need it. So I'm going to go back to here. So again, pick up right where we left off in the notes. And let's do the integral again. So it would be t minus t cubed over 3 plus t to the 5th over 5 times 2 factorial minus t to the 7th over 7 times 3 factorial plus ... That'd be from 0 to x. So here we have it with x, but remember, we're going from 0 to 1/2. So what I'm really trying to do is plug in 0 and then a half. We'll have to plug 0 when it's nothing. So let's go ahead and plug a half in to all the x's here. So here's what we have. This is our sequence of numbers. Now I realize in part C we did truncate it right here, but I wrote a few more out because it's really hard to see a pattern with only 2 terms in it. So now I'm going to look for the pattern with x's, and then I'm going to go ahead and translate it to 1/2. So I need a way to go from 0 to this, from 1 to 3s, from 2 to 5s, from 3s to 7s. Also notice that whatever n value you're at, that's what factorial you have. There's like an invisible 1 factorial and a 0 factorial there. So right away, I'm going to say, okay, I definitely know there's an n factorial down there. Now, how do I go from 1 to 3, 2 to 5, and 3 to 7? So if you sit there and think about that, eventually you will come up with the fact that in order to go to those, you're going to use the exponent 2n plus 1. So let's check it. If I do 2 times 2 is 4, plus 1 is 5, 2 times 3 is 6, plus 1 is 7. It works. And then that means I have in my denominator 2n plus 1 as well. That's a sub n. Now, we didn't have just x's in here. Our actual series is a bunch of numbers. So for x, we plugged in a half. So my general a sub n is really 1/2 to the 2n plus 1 over n factorial times 2n plus 1. So now that we did that, that's the hard part. Now we're going to go through our checklist. Now what I realized is I accidentally forgot the sign changer here. Anytime you have an alternating series, in order to make it alternating, you usually do -1 to the n to make it actually change sign. So that's a very important piece that I forgot right there. Let's go through a checklist. Now notice in the question they didn't say, hey, use alternating series error bound or use Lagrange. They just said estimate y, or explain why the estimate differs from the true value of this by less than 1 over 200. Now my estimate was 11 over 24. You should have that on your paper already. So this is the estimate. It differs from the true value of this by less than 1 over 200. So it's a really good approximation, and we have to explain why it differs by so little. So we're going to run through the checklist to make sure we can even use alternating series error bound. First of all, it is alternating, obviously. Every other sign's different, so we can use the alternating instead of Lagrange. The series is decreasing in magnitude if you found these terms as decimals, or you can just look at them. They are definitely getting smaller and smaller, the absolute value of them at least. Now we have to prove that the terms are decreasing in absolute value to 0, so I'm going to do the limit as n goes to infinity of a sub n. That'd be the limit as n goes to infinity of, now 1/2 to the 2n plus 1 is really just 1 to the 2n plus 1 over 2 to the 2n plus 1. Now 1 to the 2n plus 1 is going to be 1 over 2 to the 2n plus 1. I'm going to kick this guy into the denominator here when I write this. So the only thing in my numerator is my sign changer. So I have n factorial, 2n plus 1, and this guy, which I'm kicking into the denominator. Now, if I were to plug infinity in here, -1 to the infinity is going to be either 1 or -1. I'm dividing by infinity factorial times 2 times infinity times 2 to the infinity. So it's obviously going to be 1 over infinity, which is clearly going to 0 very quickly. So this is a check right here. So now let's actually do our error bound. So we can say, therefore, the error, which is actual minus predicted, is going to be, now my actual is right here, 0 to 1/2 e to the negative t squared dt minus predicted. So it's going to be less than the next unused term. So let's go to our prediction. Our prediction was up to the 3rd degree, which is right here. That means we cut off all this stuff, but this is the first cut off one, x to the 5th over 10. And we plugged in a half to everything, so that'd be 1/2 to the 5th over 10. And that would be 1 over 32 over 10, which is 1 over 320. Now, usually these are non-calculators, so you got to be quick at your fractions here and your exponents. And this is definitely less than 1 over 200 because I'm dividing by more. So you can conclude by saying, therefore, the error is less than 1 over 200 by the alternating series error test, or alternating series error bound. Okay, so as you can see, it's very direct. Once you go through your little checklist, just get the next unused term, evaluate it, where you're evaluating everything, and it's going to be less than that. So let's go to this one here. This was number 7. You just did this on Monday, the last time I saw you guys. Now, some of you are absent. I think 3 or 4 of you, so you didn't get this. So take a look at this. If you were here, I don't think anyone got up to part C, which is where I wanted you to get. So make sure you get up to there before you watch this, because part D uses the other parts. I think the tricky part about part A here is there's a piecewise function, and that kind of throws people off a little bit. We hadn't done a piecewise series before. So for part A, you were writing the first 3 non-zero terms for f. Now be careful, there's 2 functions going on here, f and g. Part A, all was f. So I took cosine, which I knew. I subtracted 1 from it. Then I divided by x squared. That's all this work right here. And I just called it t. You could call it p. That is an approximation for what f of x is approximately equal to. Part B is second derivative test. Check that, make sure you did that right. C says, okay, now I'm defining g to be take f, do the integral of it, and then add 1 to it. So I'm going to take this, add 1 to it, or I'm sorry, do the integral of this, and then add 1 to it. So I have that work right here. So I have 1 plus the integral of this. This is from part A. So I did the integral or antiderivative term by term, plugged x in, I add 1 to it. Now I'm looking at this. Now they set up the alternating series error test real nice for you. Watch what they did. They said, okay, go up to the 5th degree for g, then approximate only with a 3rd degree. So they're clearly setting up an error bound because you go up to 5th degree, which is right here. Then they say, okay, truncate here, get an approximation. And then this is the next unused term. It's sitting right in front of you. Now, look how they word this question here. They actually set it up perfectly for you. So you know how the last one we had to go through the checklist ourselves and we had to find a sub n. This one, they literally hand it to you. They say, okay, find an approximation using a 3rd degree Taylor polynomial. Then they say g is also an alternating series. So check. With individual terms that decrease, check to 0. Check. You don't have to do anything. It's right there at you. All you have to do is go get the next unused term in order to explain why our estimate differs from the actual value by less than 1 over 6 factorial. Again, 1 over 6 factorial is pretty small, so our estimate's good. So you're going to set up your error here, actual minus predicted. Actual is g of 1. What we really want, predicted is what we got in part C right there. Less than the next unused term. So our polynomial approximation stopped here. The next unused term was this guy right here. And it's an absolute value, so we don't really need the negative. You can't just put an x, though, x to the 5th. You have to plug in what we were evaluating when we got our approximation. Just like here, for our approximation, we plugged in a half. Yep, right there. So here we're going to plug in 1. And this is clearly going to be less than 1 over 6 factorial because I'm dividing by more. So this one they set up real nice for you. You have to actually say less than, because then that's part of your explanation. Like, don't just say, oh, it equals this. You have to clearly let the reader know that you know that this is less than 1 over 6 factorial. This was a non-calculator problem, so you don't have to actually multiply that out because this is clearly going to be smaller than that. All right, so we'll practice Lagrange more tomorrow and mix in some alternating. Enjoy your snow day. Bye.